equivalent exactly to the cache. So again, we will notice that the optimal transmission window of the BPSN protocol is based on the function of the cache. So the idea now, so cache-based transfer protocols such as BPSN can have a simpler approach to congestion control mechanism due to caching. So congestion control based on the optimal transmission window sizes as a function of cache size. So based on the previous study of getting the optimal transmission window of BPSN, so we base now the movement of the AW of the BPSN based on the two sizes, cache size plus 10 and cache size. So we have several assumptions. So the first one, all intermediate nodes have an equal cache size, caching probability, and that all packets proceed with the cache accordingly. Then the next one, the optimal good to transmission window size CS plus 10 will have a congestion beyond that point. So for the algorithm, so basically from a fixed type of window, we dynamically move it by the values by the values that the sender receives from the NAP and app. So if the sender window receives a NAP without holes and an app, so we increase the window by 2 packets. So basically, this numerical value is heuristically chosen. You cannot increase the window using a large value because of the bandwidth delay problem. So if NAP with holes is received, or NAP with holes is received, we still increase the window by 1 packet. So we cannot decrease lower than the AW or the value of the cache size. And then for the next scenario, if the NAP or the sender receives a NAP with holes and the AW window reaches its optimal size CS plus 10, so that's the time we decrease the window by 10 packets. So if else, we retain the window by its original value. So for the experimental setup, we vary the AW sizes to 10, 20, and 30 packets, as well as the cache size. So for the performance metrics based on the RFC 5166, these two metrics, throughput and end-to-end delay, are two of the best metrics that we can use once we design or to test a congestion control algorithm. So we use a linear topology to test the congestion control. So we expose all the nodes to a packet error rate of 0% and 10%. So the first one is by just implementing the DTSN protocol. And then the other one, we ingest 5 more nodes having a CBR flow of 448 Mbps. So the method of ingesting the congestion is increasing by increasing the number of CBR flow. So for the results, so for the end-to-end delay, we basically again obtain the values for the cache size 10, 20, and 30. So in general, all of the results for the comparison of BPSN and for the algorithm. So the algorithm or proposed algorithm outperforms the BPSN. And for the average throughput, so the congestion control mechanism also outperforms the original BPSN protocol. So since the BPSN protocol has a fixed window, so once we implemented the algorithm, it will already have a dynamic type of transmission window. So for the cache size 30, less are the times that it reaches the optimal throughput, since it will have a maximum window of 40. So we also obtain for the end-to-end delay gain. So the congestion control mechanism actually performs well during high PER rate and high cache size value. So for the average throughput gain, slightly better gain as compared to the original BPSN program. So for the conclusion, so the method achieved outstanding end-to-end packet delay gains, specifically at conditions where high CDR traffic flows and packet error rates. So throughput gain of the algorithm is slightly better at lower cache size as compared to the TSN. And then finally, the method is more compatible with WSM applications for lower end-to-end packet delays. So for the future work, we want to test the algorithm for a more complex topology such as multi-path topology, and also apply it to transport protocol which uses multimedia. So that's wireless multimedia sensor network. And then also to compare that to other cache-aware transport protocols such as these. So thank you.
Thank you, ma'am. So any questions from the audience? Take one or two questions. Yes.
Okay. So can you tell us which typical environment that you would use the wireless sensor device for your study?
Okay. In my study or in our study, it's not really specific where do we implement the algorithm, but normally in general, the WSM can be used in a lot of applications, especially in environmental monitoring. It can also be used in smart grid and for health monitoring also. So there are actually a lot of applications that WSM can be used. So, but in our case, this is basically just we focus on the congestion algorithm, not on specifically the application. But of course, it will affect the performance of the WSN protocol depending on the type of application. Since there is a limited memory and limited battery, since it is autonomous nodes.
Another question? Any?
Yeah, Mr. Livio, very nice presentation. My question is about the negative acknowledgement. When the sender sends a packet, so it expects an acknowledgement, but in case the receiver does not receive that packet, so it will send a negative acknowledgement. Now, how much time the sender will wait for a negative acknowledgement, or how many number the receiver can send that negative acknowledgement? Is there any number or time?
Actually, we were not able to consider the time, but that's why we measure the delay. So in our case, so we only have a linear topology. So meaning we only have one sender and one receiver. So whenever the receiver did not, or whenever the packet is not successfully received by the receiver, it will just send a negative acknowledgement informing the sender that the packet was not successfully received. So in that case, the sender now will move its window since the original protocol is having fixed window. So whatever happens to the packet, if it's lost or if it's successfully received, the window is still fixed. So you can improve the throughput. So what we did is that we dynamically move the window even if there is successful packet received or the packets were lost during transmission. So we cannot really further decrease the window because of it will affect the throughput as well as the bandwidth later.
Thank you for the questions. We move on to the second presentation. The presenter is Haidar Abdul Amir Marhoun. He is has a degree from the University of Technology in Baghdad, Master ICT from University of Tehran, Malaysia, and now he's a PhD student doing routing protocol in wireless sensor networks. The paper is the impact of data fusing versus non-data fusing in chain-based routing protocol in wireless sensor networks.
Assalamualaikum warahmatullahi wabarakatuh and good morning. while I was talking about the impact of data fusing and non-data fusing for routing protocols in wireless sensor network. So I don't, this outlines in my presentation. Everybody for introduction about the wireless sensor network. Everybody have some idea about the smart devices. All what we call the smart. That means we have some sensors for these devices. These devices need to communicate each other to deliver its data to the destination. Monitoring data or any data can collected from the environment. So this nodes can play three roles. This node can play three roles in this environment. It is maybe a base station or a chain head or sensor nodes. The sensor nodes is rules is for collecting data from environment. The chain head or cluster head or the main head is responsible to collect the data from the sensor node and deliver to the base station. These nodes are suffering from the several issues or limitation during its characteristics. One of this is the computational ability, energy resources, memory limitation, or bandwidth limitation. The most of research debate or focusing on the energy resources or energy consumption in these nodes because if some nodes deplete all energy, it will be die early and no more sensing for the environment. The power unit or the power resource, energy resources, is responsible to supply the sensing unit or on the computing unit and the communication unit. As you know, the all or the most of the power unit consumption will be in the communication unit because when to communicate one bit or to send one bit only, it need approximate what equal to 1,000 process in the process unit. So the application of wireless sensor network, everything, everywhere, what's called smart agriculture, smart city, any communication between smart nodes. These nodes need to communicate each other. So we need routing protocol to manage this communication. According to network structure, there is flat routing and hierarchical routing and location-based routing protocol. From hierarchical routing, we have tree-based, cluster-based, and chain-based routing protocols. My research area focusing on the chain-based routing protocol because during the literature it is outperformed the others in terms of fault perception and delay and the network lifetime. Sorry. From the chain base, we have according to the deployment, we have deterministic deployment and random deployment for the sensor node. For the chain-based routing protocol in deterministic routing, deterministic deployment, we have one state-of-art protocols. It's called CCM. It's 2012, and working to collect or to combine the cluster base and the chain base in the normal node and the cluster base in the chain base communication, and choose one node as main node depending on its energy to communicate to the base station. Another protocol is called TSCP routing protocol. It's 2014. These protocols enhance or improve the CCM protocols by build second stage of chain for the chain heads, and it successful to reduce the power consumption during the cluster phase in the first protocol. This paper, it is just for justify a simple thing. It's the difference between the data fusing and non-data fusing. It is not all the performance evaluation of these protocols. So if we need to clarify the difference between these two approach, the first, you can see the first chain with no data fusing. If every node have one packet to send the destination, this nodes at the end, we have 5 packets from 5 nodes. So, for example, this node number 5 or number 4 for the sending have to transmit 5 packets, and the base station have to receive 5 packets. This node have to send 4 packets, and so on. For the non-data fusing or with data fusing, every sender will send 1 packet, the other side will receive 1 packet, fusing the data with its own packet and deliver 1 packet only. So what is the difference between them? I know the data fusing is related with the application layer, and I'm working with the network layer, but this can affect the routing protocol layer. So this is what I interested to choose which approach I will debate in my research. From the second approach, every node will receive the packet from the previous node and fusing with its own data and deliver 1 packet only. So this is causing energy consumption, more energy consumption in processing unit, but low energy consumption in the transmitting unit. It is very clear between the difference between first approach and second approach. The first approach does not have this equation for the power consumption in the processing unit, and it will be at more power consumption in the transmitting unit during the first order radio model for power consumption in the wireless sensor network. The performance evaluation for the network lifetime with non-data fusing, the CCM we can see the CCM have long lifetime better than the TSCB in the non-data fusing, while the with data fusing, the TSCB outperforms CCM with data fusing. This is related with its behavior from the first. In CCM, no need to accumulate the number of packets with non-data fusing, so it will be spend a little of energy during there is no chain in the chain heads. While the TSCB have chain in the chain heads for the second stage of the chain, so it will be accumulated the number of packets, it will be consumed, it will delay more energy for the transmitting unit. While the delay is not affected by, it's not more affected by the both of approach, the CCM still outperform the TSCB in both approach. This is because of the TSCB is considered the cluster base in the second stage, while the TSCB is considered the chain base in the second stage or the second phase. And all of us know the chain base have some of delay and add more of delay for the behavior of packets. The conclusion of this paper, the energy consumption is mainly considered in all wireless sensor network, especially in routing protocols. We are doing the routing protocols because we need to reduce the power consumption. The direct connection with the base station, that means the long distance, that means the distance parameter in the first order radio model, it will be duplicated and duplicated by single hop. So we need some routing protocols for reducing the power consumption. Second, this is not big difference between the protocols if there's the researchers is interested with the delay metrics. while it must be considered of application related with the network lifetime. So somebody asked when we can use the data fusing and when we can or prefer the data fusing or non-data fusing. The answer is for it's depends on the application. For the future work, we need to design new routing protocols. This routing protocols must be consider how to construct the chain and how to select the chain head, because this is two very important things in all routing protocols, as well as to reducing the energy consumption and extend the network lifetime for the sensor nodes. Thank you.
Thank you, Haidar, for your presentation. We can just accommodate one question due to time constraint. Okay, if none, then we move on to the next presenter. Next presenter is Wail Ali Alabatle. He is a PhD student from University of Utara, Malaysia, and his paper is entitled "The Proposed Multi-Hub Leech Routing Protocol Model for Wireless Sensor Networks." Wail.
Assalamu alaikum, everybody. Thank you. My name is Wail. We propose multi-hub leech protocol wireless network. So, give some background about the wireless network. As we know, wireless network is how self-organization and wireless communication takes place. Limitation methods. Or it would be something routing in wireless sensor challenge attacks. Routing protocol in wireless sensor try to first data routing and hierarchy based routing and location based routing. So data routing is direct function DD and graphic and energy aware routing is come from location based routing. So my study it will be come from hierarchy routing, specializing low energy adaptive vessel each protocol. I will explain some about each protocol. Each protocol is the most recommended protocol in wireless sensor network. It has two assumptions. The first is that the sensor nodes are in base station, and the second is all sensor node can be sent data directly from cluster head to base station. So, as we see now, this is the base station, and here is the cluster, the node. Okay, this is the base station, and here is the node. So there is one is of the node, it will be elect as cluster head, this cluster head will communicate with the base station or sink. So there is other node, it will be node. So the node it will communicate with the cluster head will be communicate with the base station. So from base station, from sink to cluster head, we will call it inter-cluster communication. And from the node to cluster head, it will call intra-cluster communication. So, as we see just now, there is a distance between the sink and the cluster head. It's some far. This is if used. The cluster head will need more energy to send the data from here to sink. So this energy will make the cluster head will be died after some time or more because he will lose all the whole energy, so will die. So most of the researchers they think how to solve this problem. So they proposed some methods. They said first one it will be multi-hop communicate between the cluster head and other cluster head. So if we see now from here to here is very far. So if we communicate this cluster head with this, it will be more energy less than we send from cluster head to sink. And another problem is there is hot as has a hotspot problem. There is another node come after the cluster. So how we want to communicate this node with our sink? So to solve this problem, we want to communicate this node with other node, and after that we communicate it with our cluster. So for this problem, we propose some research questions. The first is how to improve the performance of our current leech protocol. We propose, where the first objective for us to how to renew design for the new inter multi-hop cluster scheme. The second will be how to design the intra cluster multi-hop as we see just before. I mean, we have to redesign the communicate between the cluster head and the base station, and we want to redesign also from the node to cluster head. After that, we want to join or integrate the two proposed scheme with the current leech protocol. So my research scope first will be cluster routing protocol, leech protocol. So how we will optimize the two. We will optimize the two intra cluster scheme, and after that we will integrate with our leech protocol. So as we see just now, this is the leech protocol, the original leech protocol. So this is how he is the okay. This is the communicate between our leech protocol. So we want to show you our proposed protocol. So we get some change from here with the cluster head. How we change this? We want to renew and re-propose a new one a new scheme how to communicate these two to
More
work
minutes.
with. So, significant of the whole study will be we will get better network performance. How? If we make more link life and more energy for our each protocol. Thank you. Any question?
Any questions from the audience? There's
Thank you. What about the performance metrics you are proposed to use in your research?
Okay. Just we're not sure here what is the performance the matrix we want to use, but for our research we want to update the last matrix because there is too many researchers did the multi-hub so the problem is they still have the same they still was still have battery low on it. So we don't show here. This will be another data.
Another question? So maybe I have a question. Are you proposing kind of simulation work and algorithms of the problem? And if so, what is it exactly that you want to implement?
Okay. Yes, actually we want to propose that I said to you that now most of the leech protocol, most research about leech protocol, how to make the leech protocol is multi-hop communicate, okay? But most of them, they look for the distance between the thing or the performance of node, or some other is looking for the battery. So our research it would be mix all, and we get the new algorithm. So we want to find the real algorithm, let's say quick research algorithm, how to find the alternative cluster hit in the.
Yeah, but just to clarify, you want still one hub to the base station, or doing multi-hub over several clusters?
I will do multi hub because single hub is not work anymore.
Thank you. Right. So moving on to the next presenter. Next presenter is Wilbert Jethro Limhoco. He is currently taking his MS degree in electronics engineering at UB Diliman. His research interests are in computer network protocols, network security, and operating systems. His paper is entitled Performance Analysis of Routing Protocol for Low Power Networks, or RPL, under an ambient energy harvesting wireless sensor network. Jethro?
Good morning. Today I'll be talking about the performance of RFCs, which means routing protocol for low power and lossy networks in an ambient energy harvesting. So first of all, a brief background on what a wireless sensor network is. A wireless sensor network is a computer network composed of tiny computers which are called sensor nodes that can sense environmental conditions, temperature and pressure, and they are powered typically by two AA batteries or smaller batteries, such as these solution Z1 modes. So as a computer network, these sensor nodes need to be routed using a routing protocol. One such routing protocol is called the RFCs protocol. It is currently the de facto standard sensor to sync, multi-sensor to one sync routing protocol for the Internet of Things. Currently has a fast network setup, about 10 minutes for a network size of 100. And it has minimal delays of about 2 to 8 seconds, again for a 100 node sensor network. And it is specifically built for low power and loss applications. The structure of this RPL routing protocol is that it creates a tree-like structure over here, right, with one sink, such as this R1, R2, and R3, and it creates a tree based on the sensor nodes A and B, and the rest of the nodes. And the tree is formed based on an objective function. And in this case, the typical objective function used by the RPL routing protocol is called the expected transmission counter ETX, which is based on the packet delivery ratio. So for the energy sources of wire sensor networks, we can divide that into three categories. The first one is the battery operated wireless sensor networks. The second one is the wireless sensor networks powered by ambient energy from the environment, the solar energy, ambient RF energy, mechanical energy, and so on, and a hybrid of those two systems. For battery-operated sensor networks, typically have a capacity of 2 AA batteries, and normally we want to prolong the lifetime of these battery-operated wireless sensor networks because if the batteries run out, we have to replace the batteries or the sensor node itself once it runs out in energy, which will happen eventually. So we have to reduce the throughput and latency in this case to prolong the network lifetime for as long as possible. But what if we have millions of sensor nodes deployed in the field, or what if we have sensor nodes deployed in hard-to-reach places? It may be impractical to replace these, or even impossible to replace the batteries of that many sensor nodes while keeping the network alive. So now we have to shift our focus to the wireless sensor network that can harvest energy from the environment. And ideally, we can maximize throughput and minimize delay in these cases. Since there is this ideal that there's no longer any concept lifetime in these sensors. But in this study, I challenge this assumption of the concept of lifetime. I thought of a scenario that what happens if these sensor nodes have no opportunity to recharge? What if there's too much traffic that the sensor nodes cannot sleep and recharge and reconnect and connect to the network and maintain the current topology existing? So what we implemented a system simulation using the Contiki operating system that uses a half-precision IEEE 754 format representation to represent the battery. Then we modify the behavior of the sensors to incorporate the behavior of charging and discharging in the sensors during the simulation. And then we perform the simulations themselves, then compare the performance of RPL running under a standard battery and running under energy harvesting scenario. So first, let me describe the behavior that we have implemented. First is, I'll describe the energy equations. The first equation is the energy consumed by the sensor when the sensor is on and connected to the network. When the sensor is connected to the network, the energy it consumes is dependent on the CPU power, the low power module power, the transmit power, and the receive power over here. And when the sensor nodes disconnect from the network, the transmit and receive radios are turned off so that the sensor can recharge, but the CPU and the low power module are still on. So based on these equations, we have created an algorithm that disconnects the sensor when it has 10% battery life left, and reconnects the sensor to the network when it has 90% battery life again. So for the experiment setup, we use the version 2.7 of the Contiki operating system, a T-mode Sky mode with a typical CC2420 module, and typical transmission range and grid size, and a randomized tree topology. And we limited the network size to from 5 to 25, intervals of 5, so that we can avoid collisions in the MAC layer so that I can isolate the behavior of RPL in terms of energy and load without having to think about the problems with collisions in the MAC layer. Then the rest of the setup is our default setting so that I can isolate the behavior of RPL with respect to energy and energy alone while scrapping the effects of other possible sources of error. That's why the packet loss, which due to that channel errors, was also set to 0. So for the results, the sensors send data every 60 or 62 seconds, and this is done so that we can for environmental monitoring applications. So what happens is, since nodes send the periodic data at roughly the same time, they will run out of energy at roughly the same time. And eventually, we will get a cluster of critical nodes in the sensor network going down at the same time, such as over here, and over here. And if the critical nodes in the sensor network are down, the entire network is down. So what does that translate to? First, the harvester network will experience severe packet drops because of this oscillating nature of the energy charging and discharging. The losses in the battery network are just due to the minimal collisions in the MAC layer, and the losses here of the harvester network are because of that oscillating nature. And since there's huge packet loss in the monitoring network, the good put will also be affected. So now the harvester network will have 40 to 45% lower good put in this scenario because of that on and off behavior. Then for the average packet delay, the packet delays on the harvester, because of that oscillating nature, the average packet delay was increased by 20 to 50 times as compared to the battery operated network. So in conclusion for this, and for future work, we implemented a battery model for the Contiki operating system so that we can simulate the energy behavior, charging behavior, discharging behavior of the sensor nodes, and we can simulate them. Then we found, then from the experiments, we can see that the standard RPL routing protocol that uses ETX as a method performs poorly in an energy harvesting sensor network because of charging and discharging at the same time for critical nodes. So as future work, right now we use a linear approximation for the battery to reduce the memory pressure on the sensor on the simulator. But eventually we will move to a more flexible operating system and more flexible simulation environment for a better and more accurate, for a more granular simulation. Then we modify our RP. Then because of the oscillating nature of the RPL in such a network, we will eventually need to modify RPL's objective function. Instead of using ETX, we will need to add energy metric. And as a reference to the first presenter earlier, we can also improve the performance of the network if we add cross-layer optimization techniques with protocols with intermediate caching, such as ETX. And that ends my presentation. Thank you. Are there any questions?
Thank you for the presentation. Any questions from the audience? Yes. The first. Back.
Yeah. Okay, I just wanted to ask you, like, after your node has disconnected, after how long does it take for it to charge and start to function again?
Right now, in the simulation, we set it to it was 1 minute and 30 seconds times 100, a scale factor of 100, so 90 seconds times 100. So that number is for the battery size. Yeah, 90 seconds times 100.
Next question, please.
Hi, Pedro. Thanks for the my question is that once your sensor starts to sense again, there's supposed to be a resynchronization in signal on when or how they can be transmitted, or is this going to be a hybrid, non-time division, uh, or time division, or non what you call it, collision detection, collision monitoring protocol that we use? So is it time division, or is it just goes into the network and starts transmitting again?
Your phrase.
Okay, sorry. Uh, Networks, they actually operate in different ways in terms of medium access. Okay, some goes by time, some goes by position sensing, some goes by different ways. So in your case, okay, once the sensor actually shuts off and shuts on again, and it turns on again, does it need to be resynchronized, or does it actually adhere to the time that actually is allocated to the node?
There's no time synchronization mechanism with this right now. So when it reconnects to the network, its rank is recalculated. So it might have a lower rank this time, like another part of the feed. And the current rank of the port is contention based. It reconnects and normal contention.
How efficient is it? How is it efficient?
Which one?
Like what is the answer?
The contention-based protocol right now for the Mac layer is inefficient. That's why I restricted the size of the network to 25 nodes. Because if there are too many nodes in the network, if the density of the network is high, or there are 200 or 300 sensors, the collision protocol will bite you, and there will be high collisions in the network, thus there will be high loss. And this is not the scope of my coverage. That will be the scope. That will be the coverage of another colleague of mine.
That was where I was coming to actually, because we are now talking about big data, and we are trying to deal with possibly more than just 35 nodes. So when you have high density of nodes, then you have a lot of collision, or in fact, if it's connection based, then they will compete for a slot to transmit. So that will consume a lot of processing power, and it does enough sort of like pick up the inventory that we have just charged.
That's not part of my coverage.
I
That's
understand.
part of the
It's part of my
coverage.
comment.
There are two approaches, but I know two approaches to resolve that problem. One is to help assist the 6-ish working group at IETF, because they're working on creating an agreement between the MAC layer and the network layer, working on a middle layer, so that the two layers will coordinate with each other to reduce the number of collisions in the channel. Another approach is modifying the trickle timer of the RTL routing protocol, but that may actually have its limits, where you have to see the final results of that. Maybe in 1 or 2 months, my colleague might be done with that. We may see that.
Thank you for the nice exchange. Okay, moving to the last but not the least presentation.
There's another question.
Oh, there's another question. All right, sorry. Okay, so this is a very interesting topic for the group. We can have this last question.
Well, there was a lot of question for that in your study is very good. Uh, when you talk about big data and sentiment, what is your next objective? As an industry, I see a value, but use cases. Since day one of this conference, I don't see any use case. your study here will be much more to it as a use case. And it is a sensor for the doors, sensor for the lifts, sensor for anything. Maybe the next stage we could talk about use cases.
The potential use case we're working on right now is to put an operating system on wireless sensor nodes that can sense current and temperature on the wire in the display. And the protocol that these current and temperature sensors will use will be this protocol, since it's currently the de facto standard. But right now, as it is, we need to improve on it because it's not efficient. It's terrible performance. We have to improve the performance and put an operating system and the modified network stack on the actual sensors once they have been fabricated. Then do actual testing of the result.
The table that you showed earlier, your experiment. What happens if you choose TCP connection?
What happens if I choose
instead of UDP?
I'm not completely sure right now, but if we use TCP and then we use an ambient energy harvesting sensors, and we still have that behavior, oscillating behavior, then since TCP likes to have a lot of knowledge packets, there's going to be a lot of loss and a lot of delay because of those knowledge of behavior. But I think it might even be worse right now.
All right, thank you. So we move on to the last. His name is Abdin bin Mod Arif. He is currently a PhD candidate in computer science at University of Utara, Malaysia. He is a former electrical and automation engineer. His research interests are in wireless sensor networks and industrial automation systems. Maybe there's a use case also in this presentation. So the paper title is WSN Signal Propagation Study in Fish Hatchery. What?
Thank you, Dr. Nestor. Assalamualaikum and good morning, ladies and gentlemen. Okay, I would like to present one of our study, that is wireless sensor network signal propagation study. Actually, this study is not yet our research. It's just a preliminary study or warm-up study for our research. So if our friends here or sister here ask what is the application, this is the application, and this is the application. And if you want to ask more application, you can ask me. I tell you, I see it as an application for wireless. Okay. When I talk to my supervisor in this, okay, actually, an application, then he tell me, okay, developing application is not telling me. Yes, right. It's not telling me. It's not telling me. But you see, if you want to try, yes. They want something computer. So what we have to do here is we have to study the performance. The performance, and we make it delivery. It's just application. Your grant will be brought to that. Your proposal. Okay. And also, there are few studies actually to develop an application for wireless network in aquaculture environment. In my paper, if you read it properly, 128 reference is all about application of wireless network in aquaculture. They develop nodes, they develop hardware, they develop the database, and all the other things. So they are not really study on the performance of wireless network. Okay. I don't like to stay like I stay inside. Most of my time, my life, my work is outside. So that's why I love to work something inside. So I did my this study actually in Ibra. Canada actually this is the biggest fish actually in the northern of Peninsula. This is the biggest one. So what is this application is about is to monitor the water quality of for the feed for the to monitor water quality for African catfish lava. Actually, before this, I just put this kind of picture in my presentation, and then people ask me, Azli, why you want to monitor frog tadpole? It's not frog tadpole, my dear. Actually, it's a fish lava for the African catfish. African catfish, in Malay, we call it as ikan keli. Very nice, right? Tasty, right? Yes. So, this actually, this thing actually can make money. And that's why we are like to involve in this industry. Okay. Why actually? Why we propose wireless sensor network? Because of there's a demand actually in aquaculture industry use wireless sensor network. Before this, I am not proposing to use wireless sensor network. After I had a site visit and I look at their practice, then I realized that yes, this is the application for wireless sensor network. First of all, what we have to know here is they take their water actually from the river nearby and it is unfiltered and untreated. Okay? And if somebody put toxic in the river, then the fish larva will die. I see it by myself. This is my experience. And I'm sitting there, I'm observing what they are doing. And what happens? They just throw it away the drain. That's what happens. Okay. That is the first demand. And then secondly, actually, I thought before this is aquaculture if they just put in the fish pond. No, actually, they put it in the fish tank. And in this area, we have 30 fish tank. So to monitor it using other technology is very hard. It's very useful to use wireless sensor network. Okay. This is some information about the parameters that we have to monitor. Okay. Okay. To monitor wireless sensor network, for us, okay, we can deploy just the sensor everywhere we want. Actually, there's a requirement. There's a requirement actually. The requirement here is what we call as packet error rate. Actually, in the standard, there is stated that if you want to deploy wireless sensor network, to apply wireless sensor network, the packet error rate must be lower than 1%. 1%. So I wrote wrongly actually in my paper. If you look carefully afterwards, I put higher actually lower than 1%. Which means that if we send 100 packets, only 1 packet lost. That's actually the requirement. And also, this is just the how to conduct the test. But actually, this is a standard that has been stated in the standard, and it has been adopted by the industry also. If you look at Siemens, what is the product? Siemens flow meter. Siemens flow meter actually they put 1%. Otherwise, don't use this kind of technology. Okay. Why we conduct study? Because of we want to see whether suitable or not use wireless network in area, in aquaculture environment area. We don't want to assume. We base on facts and figures for our action actually. So why? Because of we see there's a potential for multi-pass failing effect. Multi-pass failing can cause can increase actually the packet error rate. Therefore, there can source of reflection. We have sharp edges, source of refraction, and also is water pipe. Water pipe is everything. It's just small thing. Yes, but we have 30. 30 actually is a source of scattering. So objective of our study is to study signal propagation characteristic in fish hatchery environment and to determine, after we study that, we determine to deploy or not to deploy, to apply or not to apply. Actually, that's what this study is all about. Okay, I use simulator. I use testbed. And I love to program testbed. I not degrade the simulator, right, or simulation work, but I like to do it. I think it's better to do it in a testbed rather than simulator. Okay, I'm using microchip. This mode is called NETAPPS from microchip technology. Okay, this is the scenario actually. How we conduct propagation study, we only use two nodes. Right? We put somewhere else, then we measure. Okay, this is the fish hatchery environment. We have around 50 tanks. They range nicely. Okay, this is just the distance. Then actually, what am I doing here is, I just collect the data first. Send all the data to the point, and then I collect all the data, and then after that, I measure it offline. It's not online measure, it's offline measure. Okay, and actually to analyze signal propagation, there's a lot of method. There's a lot of method. What am I doing here is I combine it. Why? Because of it's hard for me to compare from one study to another study. It's hard for me. So what I do is I just combine, and then we easily for us to compare. And also when we combine it, we can see there's a relationship basically, and that's another information to us. Okay, I will not touch on this because if you ask, then I'll tell all about this formula. You don't know what I mean? Okay. Okay. We straight to the conclusion. The conclusion is all the packet error rate is lower than 1%. And also, actually there's a law of propagation signal that is much the distance is increased, the signal propagation power, the power is decreased. So we can see in this area actually is decreased proportionally into the distance. And it's okay. And also the data actually, you can analyze speed to normal, price and value. Okay, my research actually is related to Mr. Haidar's work. And Haidar actually we must work together. In fact, our supervisor is the same. I can help you. If you ask me about how to pop the chain, right? Actually, my study is related to that. Okay. I can tell you how to pop the chain. Okay. Is there any question?
All right, for the presentation. Any questions from the audience? Yes.
You said you analyze the results offline.
Offline, yes.
So, like you mentioned before that if someone puts some poison in the tap or water and they will all die. So, like your study, so if someone does that and so what I'm trying to ask is how useful is the monitoring of the water quality? Suppose if something like that happens, isn't there a way to monitor it in real time, or maybe that can be future work?
Okay. You must understand this study is a signal propagation study, not sensing study. Sensing study is material time. If this data actually is we analyze the electromagnetic wave that we send, the signal that we send, how is it? So no need to do real time, right? Unless you are studying sensing. That's related to sensing. This is related to signal propagation. How good our transmission is. That's the difference. Okay, another question.
All right, another question. Maybe just a short question. You just did a test with one transmitter, one receiver. So how do you think this will change with multiple sensor nodes in the study area?
Actually, we are not put it in one place. We put it in, I select around 4.
Yeah, but with more nodes, then you have interference, so that will actually degrade the performance.
To study signal propagation is point to point. That's the rule. Something one to one. If more than that is not considered as signal propagation, it's something related to network. So signal propagation is only one to one.
So no other questions? Thank you for all the presenters. So now we present the certificate. Melchizedek, Alipio. Haidar, Marhun? No, not here. Okay. Okay, you. Wail? Wail. Wilbert, Lemopo. And Maud, are you?
Thank you, Dr. Nectar. All right, now we shall take a half an hour break. Okay, and when we come back, we'll go for the next session. The next session shall be led by show. Yes, all right. So we shall come back at 2 hours, okay? And then when we come back after lunch, we'll be having a industrial talk as well, and the second keynote from Professor Neil Dyer online. Okay, Professor Neil is telling me from ID. Okay. You all listen. Yeah. I want to understand.